How you doing? Today we've got the up close and personal view into my domicile, and we'll be going over a couple of problems from your textbook. Once again, that is University Physics. It is the 13th edition, Young and Freeman. We're going to start in, we are in chapter 22, Gauss's Law. We're going to start with question 15. So 2215, and I've got the pertinent information on the board behind me. I encourage you to go look into the problem and see exactly what we're doing. But essentially, I've got some infinite wires. They tell me that I have a linear charge density of 5.2 times 10 to the negative 6 coulombs per meter. They actually give it microcoulombs. And I'm looking for a force on a specific section of wire, one wire to the other, and that section is 0.05 meters long. Now, one of the problems with this, or that students perceive, is that the wires are infinitely long, and that's actually okay. It doesn't really matter. We are obviously going to exploit some Gauss's law. So I know I'm looking for force. So the first thing that I want to do, sorry, I'm kneeling on the floor here. First thing that I want to do is my force equation, obviously, and I know that a force is equal to, can you see that? Yes, you can. Is equal to an electric field times its charge. Now, how is that actually going to help me? Remember, we're really trying to exploit Gauss's law. I was looking for my black marker here. We're trying to exploit Gauss's law. Now, what is Gauss's law? Gauss's law is all about flux. So if we remember, flux is that like flowing electric field, or my flux, so to speak, there you go, is equal to what? The antiderivative about the surface of E dot dA. Now, I apologize. All those guys are vectors. We need to keep our vector form. So what are we doing with that? Now, how am I going to take the area of some infinite thing, or I should say that dA, some small area of some infinite thing? So I'm going to actually just do this nice and slow. It should be coming, it should start to becoming easy at this point. Sorry for my bad English here. So my antiderivative of E dot dA, what is that actually? My E dot dA, that dot product, is actually just E times A times cosine of theta. And now that theta was the angle in between my flux and my my vector dA, right? And in this case, they're going to be what? Perpendicular, because I want the flux to be perpendicular. I'm looking for that maximum force. My lines are parallel. The maximum force is going to be because of that perpendicular force. So what is that A? What is my area of this infinitely long thing? Well, the surface area, don't forget, I'm not looking for an area, I'm looking for a surface area. So that surface area, come on back here, E times area, well, the surface area of my line of charge is 2 pi r. What's 2 pi r? That is the circumference around times the specific length of that wire times the height. So this right there, that 2 pi r, that is my area function. And now that is just times my cosine of theta. So I still haven't done anything except for put it in something that I can, or put it in a form that I can use. So this is one side of my flux equation. What's the other side of my flux equation? Remember, flux is also Q enclosed over epsilon 0. Well, how is that helpful? How is that helpful? Well, let's see. If I can say flux and flux, I can set those guys equal to each other. So now I can say that E times 2 pi r h times the cosine of theta is equal to Q enclosed over epsilon 0. And that is my full Gauss's law. I'm kind of stuck until I remember that I've got this linear charge density. How is this linear charge density going to help me? Well, linear charge density is charge per unit meter, and I've got a charge right there in a coulomb. So I need to rearrange that. So let's see, if I know, get a different color here. Let's get a sidebar of lambda is equal to charge per unit height, right? Because here I'm just using a length, but instead I can change length to height. That means I can say Q is equal to lambda times h. And now I've got something that I got cooking here. I've got my electric field times 2 pi r h times the cosine of theta. That's going to be equal to what I just figured out here, lambda times h, divided by that constant, my vacuum permittivity of epsilon naught. Well, I know I need my electric field, so I'm going to rearrange here. I'm going to set electric field, do some math in my head, equals to, I can just bring that whole thing over lambda times h over that whole thing, right? So I can say, I'm going to say lambda times h divided by a whole mess of stuff. 2 pi r h, 2 pi r h, cos times theta times an epsilon 0. And we should, in the way now, let me go to the other side. There we go. So we should see that my h's can cancel out right there. H and H. And what's going on with that cosine 0? This is a hard error for me to talk. What is going on with that cosine theta? I said cosine 0, I believe. Cosine theta is going to be my maximum, right? That cosine theta is cosine of 90. Cosine of 90 is going to be 1. So really, I'm dropping that out of my equation because I'm looking for that maximum force. Again, they're parallel. So now I'm left with my electric field of just lambda divided by 2 pi r epsilon 0. And now, last thing, how is that helpful? Lambda is equal to, if I have my electric field, and I know my force is electric field times Q, again, I'm going to reutilize that. All right, sorry about that jump. I just needed some more space. So from the last board, I rewrote my force as charge times electric field. We just solved for this electric field here. And recall that lambda, my charge per unit length, is 5.2 times 10 to the negative 6 meters. 5.2 times 10 to the negative 6 coulombs per meter. So how are we going to utilize this information to find that force? This is another jump, another kind of physics trick. They told us something we haven't used yet. Can I see the orange? Yes. They told me that I'm looking at a length of 0.500 meters. Yeah, you definitely can see that. Wait, sorry. I think that was 0.05. 0.05 meters. So I'm looking for a unit of length on those wires, remember my parallel wires, that are force on that section of wire. Well, because lambda is coulombs per meter, and I have this specific length, I could figure out actually my charge, Q. So my final formula, what I'm trying to find, that force, is equal to my electric field, which we just solved as lambda divided by 2 pi r epsilon 0, times my charge, and again, I don't have a charge, but I have a coulomb per meter times a specific length, unit length meters. So it's really times lambda times 0.0500 meters, or lambda times L. And if we throw that into a calculator, let's see, I've got 5, 6, 2, sorry, pi, times my radius. What was my radius? 0.3 times 8.85 e negative 12. Multiply that by 5.2 e negative 6 times 0.05. And we should get a force of 0.08, that doesn't say 81 newtons. They asked for magnitude, so I don't care about negatives or positives, though I do believe I didn't drop anything as I went through. That's all I have with this example. We'll get to more, I'll get to a few more, I believe, today. Feel free to like, click, or subscribe. And in case you were wondering, the cage in the back, that's where my sugar gliders live. You know all about them. Thank you, and I should say you'll see me next time.